And so what I've been demonstrating in my work is that when you look at my actual work and you look at these manifold of purifications, they function as the macrostates. They function as the coarse-graining of gamma states. Okay. And the equilibrium macrostate just so happens to coincide with maximum entanglement. Uh-huh. So what it's saying is that the universe evolves to maximize entanglement. And when you take this previous result of the fact that composite Hilbert spaces, and you look at the actual space, and the vast majority of it consists of maximal entanglement, you know, as far as I can tell, no one has an explanation for that until I come up with my coarse-graining. My coarse-graining explains it exactly what's going on. It's thermalization.
In an experiment, that's like decoherence with the environment, and then now we're mixing. Okay. So, okay, then what follows from that?
So that process of this thing decohering is a thermalization process. So here's the kicker of all this. So remember I said that you have a triangle in the base space, and then you have a composite space. So keep that sharp in your mind. There are two spaces, the base space and the composite space. The higher dimensional space and the lower dimensional
together, space. Right? They're correlated with each other.
Yes. And this is what's important, is that by doing this, I'm creating a coherent mapping from one to the other. Mapping. When I say coherent, I mean the information is preserved from one to the other.
Okay, yeah.
And so by taking a point on a simplex, which is a density operator, and then looking at the purifications in the composite space, I'm creating a one-to-one correspondence between a manifold of purifications up here and a point down here. And so the manifold of purifications, its volume, its size, manifold of purifications, that's a representation of the information of the state in the lower dimensional space.
Yeah.
That's why it's coherent. Like if this thing has less information in it, then this thing is bigger. So the size of this thing is representing something like the coherent mapping of the information down here from a lower space to a higher dimensional space up here.
Okay.
And so what that means is that when the thing is decohering, it's moving on a trajectory in the composite space from manifolds of lesser volume to manifolds of larger volume. And so the largest volume represents a maximally entangled state.
Yeah.
And so what this is an arrow of time that says that if you allow the universe to just evolve, it evolves in a direction of maximal entanglement.
I see. Okay. Yeah.
And so within quantum mechanics, there's a very well-known result that when you look at composite Hilbert spaces, that the vast majority of the space of composite Hilbert spaces consists of maximal entanglement. Mm-hmm. No one has an explanation for this until I provided my coarse-graining. Mm-hmm. With my coarse-graining, it explains why that is, because this is an instance of the arrow of time for entanglement.
Okay.
And it's telling you that the arrow of time, the universe tends towards maximal entanglement.
But can't it be explained intuitively? Like, okay, there's more stuff happening in the universe, so then there's more stuff interacting, so there's more entanglement.
Yes, it's like that. It's the likelihood that thing will remain set. It's like if I started off with a bunch of things that are all separated from each other, and then you allow them to evolve, the likelihood that they're just going to remain separate is poor. Like they're going to start mixing together.
Yeah.
It's the exact thing of like taking a container of air and putting all the particles in a corner. You know, that's a low entropy state because, you know, but then when you allow them to evolve, they start moving all over the place and you get something that's really mixed. It's the same thing.
Yeah. But what does that have to do with the coarse-graining you're talking about?
The coarse-graining is the thing that's associated with increased entropy. So when you go back to Boltzmann's original arguments for his arrow of time, Boltzmann was trying to derive the arrow of time using classical Newtonian mechanics. Mm-hmm. So back then, you know, the thermophysics that's developing, and we're asking the question like, why do we have this entropy generation when we're trying to do work? You know, we have this generation of entropy that's not doing work. It's like a diffusion of energy. It's like, why is this happening? And so you start developing like this idea that entropy always increases. And so people are asking, is that always true? Do we have a basis to this idea and something that can be rationally explained? And so Boltzmann set out to do this. And so he tried to prove something called an H theorem, which was the case that he was saying that there is a quantity H such that if I have a container of gas, of particles, and I allow these things to just kind of interact freely, then there exists some quantity H that always increases. It never decreases. And that would represent the arrow of time. Like this thing always increases. Okay. And so he set out to model this container of gas as spheres that are interacting with each other and bouncing off each other and interacting with each other. So he makes a bunch of assumptions. He makes a bunch of conditions like the density of particles, how often they interact, the correlation between the particles. Like he makes all these assumptions to then write down a quantity called H and demonstrate that it always increases.
Okay.
But then this guy named Lockschmidt showed up and argued against Boltzmann's result because in physics, the equations of motion, the Newtonian equations of motion, Hamilton's equations, they are reversible.
Okay.
Meaning that I can take a process, like say I take a process where all of the gas is contained in a corner and I allow it to evolve. And then say that after it diffuses and everything's all like nice and uniform, I stop the process and I reverse the momentum of everything. So I take all the momentum, then I reverse everything. And then I allow the thing to evolve. According to classical mechanics, then everything should reverse back and it should collapse back into the corner.
Yeah.
And so this is a problem of reversibility. And so this is called the Lockschmidt paradox. And so Boltzmann had to respond to this because the argument is, well, if I have these assumptions and I think that there's this quantity H that evolves, well, because of this reversibility, there must exist a physical possibility of reversing all the momentum, then it collapsing back in on itself. So clearly the thing can't always increase, it has to be able to decrease. That was Lockschmidt's argument.
Yeah.
And so Boltzmann had to make a defense of his claim, and he made it a combinatorial argument. And this combinatorial argument came up with these ideas of dividing up what we call phase space. So the first phase space is the 6-dimensional phase space, which we call mu space. And so phase space itself, just to describe that tells you the position and momentum. So going back to Hamilton's equations, in Hamilton's equations, the variables, the dynamical variables for which the evolutions are happening are what we call canonical variables, which are position and momentum. So in physics, we have this idea called Hamiltonian mechanics, and the canonical variables are position and momentum. And when we derive our physical theories, we always have some sort of abstracted version of position and momentum. Like in general relativity, position is the metric tensor, and momentum is the extrinsic curvature tensor.
Okay.
And so we always have this notion of position and momentum. And so the phase space is telling you about is the space of position momentum. So when you want to look at the system evolving, you look at its trajectory through its position momentum, how this position momentum changing. And so if I have a bunch of particles, and they're in a container, then they have 3 degrees of freedom of position and 3 degrees of freedom of momentum. So each particle has an X, Y, and Z in position and an X, Y, and Z in momentum. So that gives you a 6-dimensional space to describe the position and momentum of one particle. And so in this mu space, if I have 50 particles, then there are 50 particles in this 6-dimensional space. And the actual evolution of the system would be the changing of the position momentum in this 6-dimensional mu space of every particle. But then you can construct something called gamma space. And gamma space is a 6 times n dimensional space where n is the number of particles. So you have 6 degrees of freedom for position momentum. And then you have dimensions is that multiplied by each particle in the system. And so this gamma space, a single point in gamma space, represents all of the trajectories and everything of a particle in mu space. So in mu space, you have 1 point in that space for each particle, and in gamma space, you have 1 point for each system. So all the particles get condensed. The information about all the particles gets condensed into 1 point that is moving along in the 6n dimensional gamma space.
Okay.
And so I'm saying all of this because Boltzmann, to refute or argue against Lockschmidt, he said, let's take mu space and subdivide it, and just make a uniform grid and subdivide it. Okay. And when you do that, then each of the particles of the system is going to fall into a cell, where a cell represents a position and momentum vector.
Okay.
And then and so from this, he's able to make a combinatorial argument where let's say that all of them are in one box and only one of them is in. So there's 2 cells. All the particles are in one cell, and 1 particle is in this cell. And because the particles are indistinguishable from each other, I can take 1 particle, put it back in here, take out another one, and put it in here.
Okay.
And because they're indistinguishable, then that's equivalent. That's an equivalent thing. You can't actually measure a difference when you're looking at things like macro data, like temperature and pressure and stuff like that. That's the same thing. And so when you look at the number of ways that I can take a particle and swap it out like that, that's far smaller than if I took the particles and I uniformly distribute them through the cells and I started exchanging all of them.
Yeah.
Like the number of ways that the system can find itself in a uniform distribution of cells is significantly larger than if they're all crumbled together, like in the original example.
Yeah.
And so what that does is it takes mu space, and it says, okay, if I take mu space and look at all these different ways I can change them, and then I look at what that looks like in gamma space. What this does is this subdividing of mu space this way does a coarse graining of gamma space. Now, so think of mu space as being the triangle, and think of gamma space as being the composite Hilbert space.
Yeah.
And so what this does is it creates a coarse graining of gamma space, and of a volume in gamma space depends on the number of ways that I can rearrange this system.
Yeah. It's a high resolution, lower resolution kind of thing.
I mean, it's associated with the fact that when I look, it's associated with the fact that this idea of everything being crumbled up in uniform and like being not uniform, that's associated with think of that as putting all the particles in a room, in the corner of a room. If you let it evolve freely, it's going to uniformize everywhere, you know? And so that's a very low entropy state. So all the things, and so that low entropy state in mu space corresponds to a small volume in gamma space. And the uniform distribution represents the largest volume. And so when you allow a system that's in a low entropy state to evolve and uniformize, then its macro characteristics stop changing. So it's like its pressure and all these things and temperature, all these things start becoming constant. So that's called reaching equilibrium.
Yeah.
And that's the thermalization process. The thermalization process is to start from a low entropy state. What was I saying? Yeah, so this idea of starting from a low entropy state and going to a high entropy state, where you reach equilibrium, that is called thermalization. And so what it looks like in mu space is that you start off from all the particles being in like a single cell to them being distributed throughout the mu space. But what that looks like in gamma space is starting off from a volume that's small and moving to a large volume until you reach the volume with the maximum size. And that maximum volume represents equilibrium.
Yeah.
Because it's so big within Boltzmann, like with like arguments of Boltzmann, that equilibrium thing is so big, it takes up like 99.99% of the space. So it's like the probability that the system will be found in that state is so high. And that's his response to Lockschmidt. His response is, these other things you say are possible, but when you look at all of the ways this system can order itself, those make up 0.000000001%. So the likelihood that you're going to see it is nothing. And instead, the likelihood is it thermalizes, and then once it finds itself in this larger state, it just floats around in there because it's almost impossible to get out. Like the likelihood it'll get out of it is so low because it takes up 99.99%. So that's the main characteristic of Boltzmann's argument for the arrow of time, is that the volume of this gamma space of equilibrium is so large. And so what I've been demonstrating in my work is that when you look at my actual work and you look at these manifolds of purifications, they function as the macrostates. They function as the coarse graining of gamma space. And the equilibrium macrostate just so happens to coincide with maximum entanglement. So what it's saying is that the universe evolves to maximize entanglement. And when you take this previous result of the fact that composite Hilbert spaces, and you look at the actual space, and the vast majority of it consists of maximal entanglement, as far as I could tell, no one has an explanation for that until I come up with my coarse-graining. My coarse-graining explains it exactly what's going on. It's thermalization. This is why I keep trying to tell people, it's like, I think what I found here is actually deep and profound. Like I really do think that I've discovered something that is very, very important.
Yeah.
And I need to communicate it to people.